I solved this problem for my students the other day, and I actually have two different proofs that I want to show you, and I want to know which one you like more and why. So perfect squares are numbers like 9 or 16 or 25, just things like 3 times 3, 4 times 4, and the claim is if you add 2 to any of those numbers, you will not get another perfect square. So let's set up our notation. We've got some integer n. Let's assume it's k squared for some positive integer k. And now both of the proofs I'm going to show you are proofs by contradiction. We're going to enter a weird fantasy realm where we suppose that n plus 2 is a perfect square. We develop that and we somehow reach a contradiction. You can see that's what's going to happen below me. And in the first proof, what we start with is saying, well, n plus 2 is bigger than n. And so if we're squaring j to get this number and we're squaring k to get that number, well, that must mean that j has to be bigger than k. And since we have integers, that means it has to be at least k plus 1. And when we work through what this means, we wind up getting that k has to be less than or equal to 1/2, which is a problem because k is supposed to be a positive integer, and there just aren't any that are less than 1/2. We have a really clear contradiction, and that means that somewhere we must have made a mistake, and it must be this orange part here in supposing that n plus 2 was a perfect square. The other way to solve it proceeds in exactly the same way, but instead of using inequalities, it just uses some substitution. So if n is k squared and n plus 2 is j squared, then we must have this equation here. And after doing some rearranging and factoring, we see that 2 is going to be the product of this number times this number, and those both have to be integers. And since j and k are positive, they have to be positive integers, and so one of these factors is 2, one of these factors is 1. And now we just go through the cases. J plus k either has to be 1 or it has to be 2. J and k both can't be positive integers if they add up to 1. And the only possibility here would be that j and k are both equal to 1. But then that would mean that j minus k would be equal to 0, and that's not going to multiply to give us 2. So contradictions all over the place. This is just not going to be possible. In case you're curious, this was the one my brain came up with first, and then I thought about the other one a little bit later. I want to know which one you like, or if you have your own proof of this fact. Thanks for watching.